Hi everyone, we are back and we are going to go through our lecture 6, how we work with strain gauges and Wheatstone bridge and kind of connect the signals that we see from a strain gauge as part of kind of this instrumentation that we'll use to measure strain and actually potentially even, correlating that to loads and stresses and all that good stuff. So make sure you have a nice, good background in material science and material mechanics, and then we'll go ahead and get going, as well as kind of some of the essentials from like a circuits class. I think those are really, really critical, but we're going to go over them together anyway. So why don't we just use, basically, how do we measure strain? There's a whole history of essentially how we try to measure strain. So sometimes there's optical, and actually you can kind of see this with an old, there's these old materials that are, if you put them through cross polarizers and you strain them, you can actually see them visually. Like you can see strain. But how do you actually measure it? So the first, basically, we can correlate basically this change in resistance, and there's a long history behind it. The change in resistance of wires as you subject them to mechanical load. So you can use the change in resistance, but it's not really enough in order to kind of measure the strain that we're looking for, especially you're looking at hundreds, basically 100 micrometers or 100, not micrometer, excuse me, because strain is dimensionless, but 1 times 10 to the minus 6, strain values. You can't use that. There's no resistance measurement directly that will enable you to get that precision, but you can actually connect those change in resistance to circuits, and then you can actually get that that sensitivity and the resolution that you need to measure those. So there's lots of other cool methods. We have, in our lab, our video extensometer. And so there's lots of ways that you can actually do that. But strain gauges are still used a lot, despite some of the pain that goes into actually applying the strain gauges, as likely you won't see in your lab, but I've already done it for you. But believe me, it's not fun to kind of apply the strain gauges. But anyways, especially if you don't have a lot of the funds to use the good epoxy kits. But again, we're getting off track. So wires, when they elongate, our resistance of basically some wire, cylindrical wire, that has some diameter, that has some length, L, we can kind of see here that there's a resistance, and that's equal to, resistivity. Again, this is a material constant. C is just a constant as well. But it's basically it's proportional to length over my diameter squared. So as I pull here, my material elongates, but the wire's contracting here. So you can kind of see this L increases, my diameter gets even smaller, right? So that blows up, essentially, the resistance is going to increase. Conversely, if I, basically decrease it here, and why does the resistance increase? Because you're giving it less room, right, for those electrons to kind of travel. If I compress my material, length decreases, so this gets lower. My diameter actually increases because, again, Poisson's ratio. And now we can see why electrons have more space, essentially, to move through. Now, we're interested in when the resistance is changing. So let's see how the resistance changes as a function of some of these parameters that we talked about. So we're going to use our old friend, the chain rule, do partial derivatives with respect to resistivity, length, and the diameter. And you can kind of just walk through this. I have our Mathematica notebook, and we kind of walk through these different things. But a lot of this is just algebra and rearranging some signals, or rearranging some material parameters, effectively. So, but this is the picture that we're looking at. So we are actually pulling in that one direction. So when you do those partial derivatives in the chain rule, you can divide out by R, and now you're starting to have an expression that's a little bit more meaningful. So this is the change in resistance over the resistance, change in length over length, change in diameter over diameter, and rho over rho. Now, if we have this scenario here, well, what's the strain in the one direction? It's my change in length over my initial length, which is effectively this right here. So this is our strain in the one direction. What about our strain in the two direction? And this is, again, where we need to have a strong knowledge of materials. So remember, we're doing epsilon ij equals 1 over E times 1 plus nu sigma ij minus nu sigma kk delta ij, and then plus alpha delta t delta ij. So here, there's no change in temperature, so that's fine. If I want to write out the strain, the 1,1 is going to be equal to 1 over E times sigma 1,1 minus nu sigma 2,2 plus sigma 3,3. Now, what is sigma 2,2 and sigma 3,3 here? 0, 0. So that's how we can basically relate stress and strain here. And in this instance, that's going to be that change, that change in strain. And you can rewrite it as well. Now, what about the strain in the 2,2 direction? Well, as we pull, the strain in the 2,2 is going to be what? 1 over E sigma 2,2 minus nu sigma 1,1 plus sigma 3,3. This is 0. This is 0. So really, it's just that Poisson ratio. So we know as we pull in this direction, it is going to be, my Poisson ratio nu is equal to minus the strain in the 2,2. So it's the contraction over that strain in the 1,1. And you can rewrite it and basically get some of those values. But we know that change in that direction will just be, as well, the change in my distance over that distance. And we can kind of see that right here. And then you see here is minus E22 over E11, which is everything that we've kind of written out here. So that's how we're correlating essentially these values. So again, make sure you have that material science background. So now we have something that looks pretty cool. We also can define essentially the gauge factor. The gauge factor is typically going to be a constant. You can actually find it when you buy a strain gauge. It gives you that gauge factor, but you can also find it essentially from doing this type of experiment as well. You can calculate that gauge factor. But at the end of the day, when you rearrange essentially these expressions, and the expression in here as well, you're going to get, once you should make this definition, the strain is going to be equal to 1 over the gauge factor times the change in resistance over that initial resistance. So that is really, really, really critical. So that's the kind of key idea that we're looking at here when we're calculating essentially that strain. So excellent. So you can kind of see, and remember, we're looking at when you have a strain gauge, we're typically going to draw it just like this little box. The wires are in this direction. So again, if we're pulling along here or compressing it, we're looking at the change in the length essentially of those wires. Now, what's happening in this direction, how will it affect the wires basically along this direction? That's kind of the key idea here. So we're always looking at strain gauge, measuring it in that direction. Fantastic. Now, again, we don't have, this is kind of what we talked about previously, we can't measure it just with an ohmmeter or like with a multimeter. So we actually have to leverage this kind of idea of circuits in order to kind of make meaningful strain measurements, because we really can't, this is an important equation, but it's one where you're not going to use significantly unless you're doing like kind of a specific calibration, a shunt calibration. We'll come back to that in a bit. But we need something where I want to correlate strain to some type of change in voltage instead. So I need to kind of convert this change in resistance to change in voltage. And we're going to do that with some voltage divider circuits. And then we're going to do that as well with some Wheatstone bridge configurations. So see you in the next video. Thanks. Bye.